Newton comes up one more time for us in this lesson. Um, because there's a formula for Newton which is very similar to the formula for Coulomb. It's a very, again, it's to do with fields as well. So some physics books would put this lesson in their mechanics section, but most advanced college books would put this section I'm doing in the field section, which is what we've done. So this here, Newton's law, that's not the full title, Newton's law of gravity. This, if you go to a college or an A-level book, will be in the field section of the book. A high school physics book might put it in the mechanics section. Okay. Newton's law. Okay, got that? Yeah. Right. Okay. So as you know, the Earth pulls other masses to it, and the Sun pulls the planets towards it, such as the Earth. Therefore, there must be some kind of field, like an electric field or a magnetic field. So if you think about it, if this is a magnet, and this is a charged particle, you know when the charged particle moves perpendicular to the magnetic field, it will experience a force. Or simpler, if this was negatively charged and this was positively charged, what will happen to them? They'll attract to each other. And there's some field in between the two, and this is how they attract. And this field you can't see, but we can draw the lines for it. So we imagine that the field, you could see it. It would have lines going from the positive to negative, isn't it? No, negative.
Positive and negative.
I'm so confused. We draw our lines positive to negative. So yeah, we draw the field out like this, and there's the negative one, and its field is going in. Anyways, there's an attraction between them, and this force, we have the formula to calculate this force. This is Coulomb's law, which we had in the last lesson. So if we have something like the Sun, and we have something like Earth, and it's moving around in an orbit, and there's a force pulling the Earth towards the Sun, and in fact there's a force pulling the Sun towards the Earth, there must be a thing causing this. There must be some kind of field. Now we know it's not an electric field. Electric, no, because there's no voltage here. The Earth's not connected to a battery. There is a magnetic field around the Earth. You know this. There's a magnetic field around it, and I think there's a magnetic field around the Sun as well. But this is not what's causing them to attract. It's not this force here. So there's another field which is a gravitational field. So we imagine it's a field, and it's a gravitational field, and it's not just around the Earth, it's around any mass. And it would look something like the picture below. So everything is attracted towards the Earth. So if you're standing here, you will be pulled towards the Earth. So there's a gravitational field around the Earth. And likewise, there's equipotentials. And we kind of already have an idea for potential energy. What's the potential energy formula? It's mgh. So again, it's not surprising that the locations where the height are the same is where the potential is the same, because potential energy is mgh. So it's not surprising that the equipotentials look like this. And notice that the field points towards the center of the Earth, and again you kind of know this already, that things are pulled towards the center of the Earth, so none of this should be too surprising. But we're going to think about the gravity force as a field. That's how we're thinking about it, okay? So what I want you to do is just to draw the field and equipotential diagram for the Earth's gravitational field. So just draw that diagram. So the black arrows are the field lines and the red circles are the equipotentials. The black arrows are the field lines and the red circles are the equipotentials. Yeah, the black arrows are the field lines. How come? Say again? The red circles are the equipotentials. You know what I mean by equipotential? Yes, you know equipotential? Yes. Okay, can we go on? You have this drawn? Yes? Okay. Right, so this was discovered, it was discovered by Newton that masses attract other masses. So this is gravity, no surprise there. And the bigger the mass, the more force there is, and the closer the masses are together, the more force there is. So in fact we have this Newton's law of gravity, F equals G m1 m2 over r squared, where F is the gravitational force, force due to gravity, between the masses of m1 and m2, and they're separated by distance r between their centres. Now I should point out, usually one of the masses is very big and the other mass is very small. So sometimes I would use a small m and a big M instead of m1 and m2. Or some books might have small m, big M, but the formula is the same. It's mass 1 multiplied by mass 2.
But we don't have consider.
We do. It's just the force is so small, you can't measure it. You have to have a very big mass. But no, you are right. So you can do physics experiments with really sensitive equipment where you have like maybe 1 kilogram lead weights and you hang them on very fine strings, and there's a very sensitive machine that can measure the force between them. And even though the force is tiny, it can just about pick up the force that's pulling the two masses towards each other. I'm simplifying the experiment, but it has been done. So it's difficult to imagine that there's a force pulling these two together, but there is, it's just that it's so small. And the reason it's so small is because the G in the formula is so small. See? So you would need masses in the scale of 10 to the 11 to be able to cancel this 10 to the minus 11, you know. Well, maybe not 10 to the 11. You need masses in like 10 to the 5 to be able to cancel out how small the G is. So you won't really start measuring the force until the masses are at least 10,000 kilograms or 100,000 kilograms, at least 100,000 kilograms. Then you can start measuring the force.
I just need to minimize sorry, G.
Hmm?
I just need to minimize the G. That's all.
Minimize the G?
Yeah.
What do you mean?
To make it less than this value, and then like each mass attract the other easily.
Yeah, well, we wouldn't say minimize the G. Yeah, you want to cancel out the G. So if the masses are big enough, they will cancel the small value of the G.
Yeah.
Uh, and the units, of course, are newtons, meter squared per kilogram squared. Yes. Okay. Uh, this formula looks like what other formula? Looks like Coulomb's, isn't it? Coulomb's one is F equals K Q1 Q2 over R squared. This is why it makes sense to do this in fields as well, because even the formula is very similar to Coulomb's field force of electromagnetic attraction. Okay, continue. You got this? No. Please note the small value of G. Compare that to the large value of K with Coulomb. So I think with Coulomb it was 10 to the 9. With newtons it's 10 to the minus 11. That means there's a 10 to the 20 difference in the value between K and G. Okay, continue?
Yes.
Right. So notice how similar this is to Coulomb's law. What we've not said yet is what the field strength is. So the field strength E in an electric field was the force per unit charge. So if you remember that when we had an electric field, do you remember you had F equals QE, and this is the Q, and this can be a big Q. Remember that the E was F over Q. This is the definition of electric field strength. It's the force per unit charge. So we have this gravitational field strength, which we'll just call small g for the moment. And I'm not saying that's the same as the g we're using in no, not the capital G, the 9.8 G. And yes, it's not the same as the big G either. So mathematically, if we use the same definition, the gravitational field strength should equal F over m, just like the electric field strength was F over Q. Although we have a formula for F. So Newton said F equals G m over R squared. So if I put Newton's formula in for F, I'll show it to you here. So G equals F over m, which equals G m over R squared over m, where we have a small mass and a big mass. So we have a big mass and we have a small mass, and it's being pulled towards here. So this would be G m over R squared. That's the gravitational field strength at a distance r. Again, look how similar this is when we did electric field strength for a point charge. I think I said the formula was kq over r squared. And you remember the other one was E equals voltage over distance between the plates. So again, we can make a comparison with the electric field lesson. Yeah, we can cancel, so we get this formula, and the units being newtons per kilogram. So electric field strength G is Gm over R squared. This formula you need, of course.
So both of them give us the same result?
Yep, but the problem is here we don't, we would have to calculate the F, whereas here we just need to know the M and the R, which should be given. Yes, go on. Yep. Okay. Let's calculate how strong the gravitational field is at the surface of the Earth. So the rate of got cut off a little bit here. The radius is 6,000. So can you write that down? The radius of the Earth is 6,371 kilometers. And then I need to get the.
3,000.
I'll put it back up here. Let's just. Yeah, the radius is 6,371 kilometers, and the mass is 5.97 times 10 to the 24. Let me just. Did you write that down? Let me just try and fit this in. 6,371 kilometers, yes, and then 5.97 times 10 to the 24
On the mass.
for the mass. Yeah, okay. Can we go back to it? Right, so let's have a look at this problem here. So here is Earth, here is person on the surface of the Earth, the distance they are from the center. What did I say it was? 6,371,000 meters, and the mass of the Earth
5.97 into times 10 24.
24 kilograms. So the gravitational field strength 6.67 times 10 to the minus 11 times 5.97 times 10 to the power of 24 divided by the radius squared, 6371000 squared, and you get 9.81 exactly.
So this is the same G.
It is. So this G here at least is the same on the surface of the Earth. So this should give you a meaning of what the gravitational field strength represents the acceleration in free fall. Now this G is only 9.81 on the surface. If you were up higher and you have a bigger radius, then will the G be bigger or smaller? Think about the formula. It'll be smaller. So near the surface of the Earth, G is 9.81. So therefore we can think of G as like the free fall acceleration. However, note G is not a constant 9.81. So it's going to depend on your height. So far we've been approximating it as constant. In fact, it has been done as an experiment, and you can actually do it yourself if you have a very accurate weighing scale. You can actually show that if you go to the top of a tall building, 100 meters or whatever, the value of G is slightly less than a ground level on the ground floor.
Jump over.
Yeah, what I'm saying is, do you remember, for example, we used the pendulum to calculate the value of G? Remember that experiment? Experiment number, no,
Number
2. I'm saying if you did this experiment on the top of a building which is 100 meters high, okay, maybe not the pendulum, a different equipment, but the idea is if you did an experiment to calculate G on the ground level and G 100 meters up, in fact the values you get will be a little bit different. So maybe on ground level the G is 9.81, and on the top floor the G could be 9.80999 or something like that. So it will be slightly less. So we can estimate the G as constant, but it's not constant. Okay, it decreases as you move upwards. Right. So just to recap where we're at, all masses produce a gravitational field which attract other masses. The force is given by the formula G(m)m/r². Fields always point towards the centre of mass. The field around a small m can be ignored when compared to a bigger m. So just like with the Coulomb's law, if you have a large mass and a small mass, you can ignore the field around the small mass and just look at what's happening to it compared to the bigger mass and the bigger field. Because masses are positive, the fields never point out but only in. So your fields always point into the mass. They never point outwards like with the electric field. And this is because masses are only positive. The strength of the field can be calculated from this formula Gm/r². And this G is actually 9.8 on the surface of the Earth. And in fact it's the acceleration due to gravity in the field. The value of G near the surface of the Earth is 9.81 newtons per kilogram or meters per second squared. Now when one mass m is trapped in a circular orbit by another mass m, then it will have negative potential energy. And the formula equals minus G(m)m/r). But you might be thinking, well, this is different to the formula we had in semester 1, where I said the potential energy is mgh.
This potential energy coming out in the exam.
Hmm?
This potential energy coming out in the exam.
This one, now you see, if I look at let me just go back to the syllabus learning outcomes.
This one you took from the syllabus?
No, these learning outcomes are from the syllabus.
So good.
Explain that close to the Earth's surface. Yeah. This one would not, the formula would not be in the exam, I don't think. There's nothing in the learning outcomes that would suggest that it was. But what I'm using the formula for is in the exam, you know. So although the formula might not be in the exam, what I'm going to do with the formula now, the explanation I'm going to give you now is on the exam. So then it makes me feel like there's a very small chance it could be on the exam in a very small way, but maybe just enough that you have to mention it. I'll show you what I'm going to do with the formula now. Let me just get back to the slide I was on. Right, so we have writing pad turned off.
You got it?
Mm-hmm.
SUDE or
Oh, that's what I wrote.
pseudo.
Come on. You can do it. Come on, turn back on. Dude. There we go. Right. So what we have here, we have our Earth. I'll draw it a bit better. We have our Earth. And we know that the potential energy formula is mgh. But that's different to the formula I just gave you. So when do we use potential energy? Or what is potential energy? So potential energy, if you start at ground level and then move up to a height of h, then what happens to your potential energy? You gain potential energy, don't you? If I move this up, it gains potential energy. So let's use the formula I just.
Gains or converts?
Well, I mean, it's given potential energy. Like it's converted. My energy in my arm is converted into potential. So it gets potential energy, whereas previously at surface level it had zero, and then it moves up and it gets how much potential energy? mgh. So it starts from here and it moves up. So what potential energy? I'll write PE gain. Well, that would be the potential energy at the top minus the potential energy at the bottom. Now we know that this is 0 and this one here is mgh, and so the difference is mgh. But I don't want to use the yeah?
Why it's not minus one?
Well, this is what I'm saying. I don't want to use that formula. I'm going to use the new formula and see what I get. Okay. So according to the new formula, I should have minus g m over radius of the Earth plus the height squared minus g m over radius of the Earth squared. This is r. So if I just clean that up a little bit, that gm I can take out. So let me take it out. Gmm, and I'll be left with 1 over r squared minus 1 over r plus h squared. Okay, so I'll just give you a minute to catch up.
What is it equal to or minus
Is y equal to minus?
the G, the one with R plus H?
Is it minus here? Oh yeah, because the formula.
No, no, no,
Minus.
not the one you first
Oh,
actually.
sorry, I shouldn't have squares in there. Sorry, let me delete those squares. Yes? KJ?
Okay.
There's a no, it's okay?
Minus, minus.
Yeah. Minus, minus. So that's the plus here. So because that's minus, minus, I just put it there as a plus, and this one here I put at the back. Okay, what I'm going to do next is take the, sure.
No squared.
Huh?
No squared again.
Yeah, there's no squared in the potential energy formula. Yeah? Now what I'm going to do is I'm going to take r out of the denominator. So this would be r times 1 minus 1 over r times 1 plus h over r. So because there's r in both, I can take that out as g m over r 1 minus 1 over 1 plus h over r. Yeah, I took this r out in front, and what I did was I took the r out of each of these. So if I take r out of this, it's just r times 1, and if I take r out of this, it's r times 1 plus h over r. So I factor out the r. Yep. Yes, can I go ahead? So what I'll do next is I'll say this is G M over R 1 minus 1 over 1 minus minus H over R. I just put in two minuses. And what I'm going to do now is I'm going to say let x equal minus H over R. And also, remember what H represents. What's H? It's the height above the surface of the Earth. And what's big R? The radius. So, is this going to be a big number, a small number? What type of number will this be? It'll be very small. The height compared to the radius of the Earth, this is very small. Very, very small. So we have here G M over R 1 minus 1 over 1 minus x.
Why is now 1 minus minus H over R?
I changed my plus here
Mm-hmm.
into minus minus.
Okay.
All will become clear in a moment. Okay, continue. So if you remember your semester 1 maths, and if you remember the lesson on long division, you know that this long division here, 1 divided by 1 minus x is equal to 1 plus x squared plus x cubed, etc. Now, this is where the magic happens. Because x is really, really small, what do you think we can say about x squared? If you have a really small number and you square it, it gets smaller. And if you cube it, even smaller. So because x is so small, when you square and cube it, these values here are so small we can just ignore them. So ignore. So we get this is roughly, although it's quite accurate, GMM over R 1 minus bracket 1 plus x. Close bracket there. Well, that's handy now because what happens to the 1s? They cancel.
Mm-hmm.
So you're left with GMM over R 1 minus x. But what did we say x was? Minus minus h over... Oh, sorry, why did I write the 1 in? The 1's gone. Minus minus h over big R.
Why? Because it's plus now.
Oh, minus x, because minus x here.
Okay.
And x is minus h over r. So now it is plus, you're right. So this is g m over r h over r, which is equal to g m over r squared m h, because the r is multiplied. Or if you want, that's m g m over r squared h. But what's g m over r squared? That's the gravitational field strength at the surface of the Earth. Otherwise known as what letter?
Known as G.
Oh my gosh.
What is that?
So that is the proof that although the formula looks totally different to the formula you did in semester 1, that if you use the formula, you'll get the same answer as the MGH formula. Yes? And I think this proof is interesting because from the beginning, you wouldn't have guessed that you will end up with the same formula, MGH. But we've actually shown that you can get the MGH formula from the new formula from today. Meaning that if you use the new formula, you still get the same answer. However, the advantage of the new formula is that it works for any radius. Whereas, when can you use this formula? On the surface of the Earth only. Okay. Right. Back to the slides. Yes. Yes, we don't, but I've just proved that the formula is the same. So Newton's law of gravity gives the size of the force between two masses. This force, the force between masses, is one of the four fundamental forces of nature. So there are four forces in nature. We've just seen one of them, Coulomb's force for attraction between the charges. Newton's force for gravity, attraction between two masses. Again, it's an example of an inverse square law. And before we look at some examples, please note it's important the fact that G is very small. Compare that to the K, which was very big. Okay, so let's have a look at an example here. So what is the force of attraction between the Earth and the Moon? I give you the mass of the Earth, I give you the mass of the Moon, and I give you the distance between them. So I'd like you to try this first. You have the formula, F equals G mm over R squared. So I want the force here, so I'll calculate it too.
Over R squared?
Yeah.
And what's the G?
The big G,
Yeah.
it's a constant, same always, 6.67 10 to the minus 11.
You need to change this in kilometers into meter, no?
We change kilometer to meter?
Oh yes.
2.2,
What did you get?
2.2
10 to the
minus 3.
minus 3. You know that's way too small. It should be big force between them. Okay, let's have a look. So here, so you have F equals G, mass of the Earth, mass of the Earth, mass of the Moon divided by the distance squared. So look, when I put in all my numbers, I get 1.97 times 10 to the 20 newtons. I just type it in on the calculator. So I have 6.67, 10 to the minus 11, 5.97, what's that, 10 to the 24 is it? Times 7.32, 10 to the 22 over 385,000,000 squared, and I get the answer.
Okay.
So just put the numbers in on the calculator. Did you get the same, KJ? No, what did you type in?
6.67 times 10 to the minus 11.
Yeah.
5 times 9.7 times 10 to the
5.97
yes
times,
10 to the 24.
yeah, next, Yeah,
and
one sec.
10 to the 22.
And the distance?
3 million.
385,000,000.
385 0 0
Did you
0
get
0
the
0
Yeah.
question?
squared.
Squared.
Okay.
Yes, you got the same answer. Did you forget the square?
No, I put 300.
Too many or too few zeros?
I don't put 385, I put 300.
Okay. Right, next example.
1 more.
Yeah, I got it.
How long does it
How long does it take the moon to orbit the Earth? So it's the same information. I want the periodic time now. Okay.
have to use omega?
Yeah. You know that F equals m omega squared or. But you already have the F from the previous question. So you have 1.97 times 10 to the 20 equals mass of the moon omega squared or. So if I divide the mass and the or and then take the square root, I can get the omega. So omega equals square root 1.97 times 10 to the power of 20 1.97 times 10 to the power of 20. I have to go back to get mass of the moon and the radius.
7.34.
Okay, it's like 7.34 times 10 to the 22 times 385,000,000. Okay, so I have the omega. The omega is a tiny number, 2.64 times 10 to the minus 6 radians a second. The periodic time is 2 pi over omega. So that would be 2379716 seconds. That many hours. Which is 27.5 days. Or about 4 weeks. Which I shouldn't have to tell my Irish students this. They know that your calendar is lunar. So each month is based off of the cycle of the moon around the earth. So 4 weeks is the answer you were expecting to get, right?
They can be sure.
They should be sure. Because our whole calendar is based off of lunar cycles.
I don't understand that. How?
1 month is one. Isn't it 1 month is one lunar orbit?
No.
Sometimes it's 29, sometimes it's 30.
Yeah,
Yes,
because
approximately.
because it's not exactly. What did you say? Sometimes.
29, 30, on this days.
Yeah. It's not exactly a whole number of days.
It's 4 weeks.
It's 4 weeks.
Imagine if we didn't count the leap days.
We'd be off by 15 days, I think. The calendar.
15 days. That would be off by.
Or would it be?
If we skip it for 100 years.
Huh?
We skip the leap day for 100 years.
For 100 years. Well, then you'd be off 1 day every 4 years. You'd be off by a month. Yeah. All right.
So what do you call the science for the plants and all these things?
Astronomy.
Astronomy?
Astronomy. Yeah.
Astrology.
Okay. How much potential energy does a satellite have that is this distance above the surface of the Earth? Okay, try this one for me.
Same information?
Actually, I didn't say how big the satellite is. It's a 100 kilogram satellite. Yeah, so what you have here, it's a, there's the Earth, and here is a 100 kilogram satellite above the Earth. and I want to know what potential energy does it have. Okay, so I give you the mass of the Earth. I don't need the mass of the Moon. Actually, I should maybe say the mass of the satellite is 100 kilograms. I don't need the distance between the Moon and the Earth. This is extra information you didn't need to know. I'll delete it.
But do you need the distance from the Earth and the satellite?
Yes, I give you that.
See your question?
Yes, yes. Um, Radius of the Earth. What did we say the radius of the Earth was? 6371, wasn't it? Let me just resave it.
Only 6,000.
6,371
Radius of
kilometers.
Earth.
Yeah,
Sure.
isn't that what we said earlier?
Yes.
Yeah. Okay. Okay, here we go.
But the satellite is more than the ring distance.
Hmm.
The satellite is more higher than the surface of the sun.
It should be. Otherwise, you have a problem with your satellite if it's less than the height of the radius of the Earth. Okay, try this one.
Minus 6.2.
Yeah, well, you calculate and I'll calculate too and see what we get.
So what's the formulas maybe?
I gave it to you. Potential energy formula.
One
Go on, G please.
1.1 into times 10 12.
One sec. 6.67 times 10. It should be a very big negative number. A large negative number.
Minus 1.1
No,
times 10 11 12. Sorry.
no. Did you get it? So you use the formula. What formula do you use?
Um,
'MGH formula?
1.8
No,
no.
1.8 times
no,
minus 1.
no.
So GM over R.
G minus 1 minus 2.
Minus GMN over R.
Yes, isn't it?
What's the distance between satellite and the Earth?
3576357.
What did you make as the radius? What's the...
3578600.
No. Read carefully.
Of the surface of the earth.
Yes.
6731671.
Everybody's making the same mistake. The radius is not 35786. It's 35786
Plus
plus 6371. Well, I know that. You didn't know that.
I did.
Did you?
I was writing.
Yeah, sure.
So
So,
what's the answer?
so what do you get now is the answer.
35786.
Okay.
That's what I'm saying. Why are you sure about it? 600,371.
You didn't say that.
Say that.
I don't remember you saying that. I don't think you said that, but if you say so. G M over or. No, sorry, not F. P E. P E equals minus G M over or. So I got here minus 9.45 times 10 to the 11 joules, or if you want, that's roughly minus 10 to the 12 joules.
About 9365.
Yeah, roughly. 10 to the 6 is mega, 9 is giga, and 12 is tera. So this is equal to minus 1 terajoule. So because the potential energy is such a large negative number, it basically means that if you wanted to free a satellite, you would need to give it 1 terajoule of energy to free it. It's trapped in orbit. Now, of course, it has kinetic energy as well, so the picture is a little more complicated than I said, but it is still, the potential energy is a very large negative number, which is important.
Is it 11 or is it 8 to 9?
This is 11.
Check.
Got 11. Well, maybe it's wrong. No, I'll check. Sorry. Maybe I didn't convert. Oh, hang on. Yes, this is not 11. It's not as bad as that.
It should be 8. 6.
Did you get 8? You said.
Yeah.
Correct. So this here is not as big as 11. It is an 8, which makes that a 9, which changes that from tera to
0.9.
what's 10 to the 9?
10 to the 9. 9.
Oh yeah, it's not 9.45, but
9.3.
yeah, but I just want to get the power right for the size. So what's 10 to the 9? What's it called? Giga, yeah. So it's 1 gigajoule. Okay, continue.
Stop, like here.
Oh yeah.
Still no break?
Not for you. For me, yes. Not for you. So you don't deserve a break, to be honest. To be honest, you had enough of a break over the weekend when you weren't doing your physics work. So no break for you now. I want you to do these questions because when I come back after my break, I'll do these questions, and I won't be happy if you're not working. All right?
After 10 minutes.
Yeah, but are you going to work on these?
After 10 minutes.
No, you don't have a break now because you don't deserve a break because you're not doing work for me at home. You have enough of a break at home. If you're not going to do work at home, you're going to have to do it here. You can't have no work at home and not doing it in school.
Okay, let's
So you made you made a choice not to do work at home. True? True. So now for you, I'm making the choice. You're doing the work now.
Okay, I'm not saying no, but
Okay.
I break for 10 minutes and
No.
nothing to do.
No break. 0 break. Okay. Now next time, if you come to class and you have your homework done, then you don't need to do it in class, and of course you have a break. But today I want you working.